I'm Shashank Gupta, Assistant Professor in EN Department, Allen House Institute of Technology, and today we are going to perform an experiment of verification of Thevenin's theorem. So verification of Thevenin's theorem, first we are going to explain it in the whiteboard, then we will perform the experiment on the experimental kit which we have. So this is our experiment name, verification of Thevenin's theorem. So what is Thevenin's theorem? First, you need to understand what is Thevenin's theorem. Thevenin's theorem, in any linear bilateral network containing several sources and several resistances, we can convert it into a simple circuit containing a single voltage source whose voltage is V.Th, where V.Th is the open circuit voltage between the load terminals, and we can convert it in all the resistances into a equivalent resistance which we connect in series with the V.Th, which is Rth. Rth is the equivalent resistance. Equivalent resistance is calculated by open circuiting all the current source and short circuiting all the voltage source. And then we calculate the equivalent resistance looking from the terminals, from the load terminals. This is the way how we calculate Rth, and first we calculate Vth, then we calculate Rth, then at the last step we join them, Vth and Rth, in series, and at the last step we load impedance RL, which we have removed in the first step, we join it with the Vth and Rth in series with it. So to begin with, we start with step 1. I have taken the same practical example which we are going to perform. First we will solve it by calculation, then we will perform the practical to verify the calculation. So what we are doing, you must have understood this. First we are solving the whole network by theoretical method, means we are solving the Thevenin's theorem by theoretical method, and then after solving it we will perform the same on the experimental kit and verify that is our reading correct or is our reading wrong. So what we have taken a 12 volt DC source, okay, and 50 ohm resistance here, 100 ohm resistance here, and we have to calculate Thevenin equivalent across A and B. It means that A and B is the load terminal. So this is the load resistance. It is denoted by RL. So now voltmeter is kept here to measure the voltage Vth. So this is our practical kit which we are going to perform, which we are going to implement in the practical. This is the circuit which we are going to implement in the practical. Now step 1. What does step 1 say? Step 1 of Thevenin says that remove the load impedance if any. So there is a load impedance here. So the step 1, we will remove the load impedance. This is our step 1 complete. Now the step 2 says that find the Vth, find the Thevenin voltage. So how will we find the Thevenin voltage? We will use the circuit of step 1. We will not use the original circuit. We will use the circuit of step 1. By using the circuit of step 1, we will calculate the current. So in this loop we can see that the current will start flowing from here, and this is a complete loop, and there is no other loop. So this is the only single loop in the circuit which exists. So we have to calculate Vth. What is Vth now? Vth is the open circuit voltage across the load terminals. What are the load terminal? A and B. So we have to calculate the voltage across A and B. So VAB, actually we have to calculate VAB. So VAB will be the Vth, Thevenin voltage. To calculate VAB, we have to apply KVL or KCL or whatever the laws and calculations required. So starting from here, there is a single loop, so we can use KVL because in a closed loop we can use KVL. So 12 starting from the battery 12 volt, positive terminal of the battery 12 equal to. Now we are moving here and the current arrow direction is also same as our direction. So it will be written as positive 50 into I. This is the voltage drop across this resistance. So plus 50 into I. Now we are moving here. So the voltage drop here will be plus 50 into I. 0 ampere current will flow across 100 ohm because this circuit is not complete. From here there is no path for the current to flow, so 0 ampere current will flow in the 100 ohm resistance. So here 50I plus 50I equal to 12. Now calculate 100I and we divide by 100, 0.12 ampere. So current comes to be 0.12 ampere. Now we have to calculate, our aim is to calculate the voltage drop across A and B. We have already calculated current here. So 100 into 0. This means B.Tech equal to voltage drop across 100 ohm equal to 0. Now we are moving downwards, and what is the voltage drop here? Plus 50 into I. We are moving downward, arrow is also moving downward. So it is in our direction, so it will be written as positive. So plus 50 into I. 50 into I we have already calculated as 0.12. 50 into 0.12 equal to 6 volt. So the calculated voltage, our calculated voltage B.Tech is 6 volt, coming out to be 6 volt. Now second part of the question, the same question. Now we calculate RTH. Now what is the method of calculating RTH? RTH is the open circuit. RTH is the open circuit equivalent resistance looking from the load terminal by short circuiting all the voltage source and open circuiting all the current source. There is no current source here, so we need not to worry about it. Now there is a voltage source, we will short circuit it. So this we can see that this voltage source is short circuited here. Now we calculate the equivalent resistance. We can easily see that there are two ways from A to B. This is the one way and this is the second way. So it means that this 50 ohm and this 50 ohm are parallel to each other. So we will use the formula of parallel, R1 into R2 upon R1 plus R2. This means 50 into 50 upon 50 plus 50. This comes out to be 2500 upon 100, which means 25 ohms. So this calculation comes out to be 25 ohms. Now this 100 ohm and this 25 ohm are in series with each other. So the series resistance, we know the formula for series resistance, R1 plus R2. So 100 plus 25 equal to 125 ohm. So the total calculations of V.Tech and R.T.H comes out to be V.Tech equal to 6 volt and R.T.H comes out to be 125 ohm. So we form on our fourth step, we form the circuit using V.Tech and R.T.H in series with it. V.Tech is 12, V.Tech comes out to be 6 volt. So it should be written as V.Tech equal to 6 volt V.Tech and R.T.H comes out to be 125 ohms. So this is our circuit for step 4. Now for step 5. Step 5 our circuit will be, we will put on the load resistance which we have already removed in the step 1. We have removed this RL, we will put it again back. This is our final Thevenin equivalent circuit and thus our problem is complete here. But now what we have to do means we have made all the calculation which are available in the circuit. 12 volt we have taken the source, we have found the V.Tech by theoretical calculation 6 volt, by R.T.H we have found by calculation 125 ohm. Now what we have to do, our aim is to verify this Thevenin's theorem. Now we will move on to the kit and then we will measure this V.Tech, and if it comes out nearly about 6 volt, then it means that our theorem, Thevenin's theorem, is verified. Now we will perform the experiment on the experimental kit. Our experimental kit is the same as we used in superposition theorem and Norton's theorem. So this is the 12 volt DC supply. In this kit we can see that 12 volt DC supply. So we have connected it to 12 volt DC which is given here. 12 volt DC should be connected to this 12 volt DC. Positive to positive terminal, negative to negative terminal. This black wire is connected to negative terminal. This blue wire is connected to the positive terminal here. Now for this resistance as we have made in the circuit diagram on the whiteboard, this is a 50 ohm resistance. So it is, this red wire is connected to this 50 ohm resistance here and this black wire is connected to other 50 ohm here. Now the third resistance, which is also 50 ohm, third resistance is connected, this wire is connected to here 50 ohm, and this wire is connected to the 50 ohm. So the two resistance of 50 ohm and 50 ohm are connected, and the other resistance of 100 ohm, which is also connected here, R3 resistance. So this resistance, this by this wire 100 ohm is connected, and this 100 ohm is connected to the voltmeter. We have a inbuilt voltmeter in this kit. So voltmeter can measure from 0 volt to 20 volts. So this voltmeter is connected, and from this voltmeter we have completed the circuit by the third resistance. So this is our experimental kit. We have made all the connections here. Now we are going to start the kit. We have to measure the reading only. The rest all we have calculations, all we have done on the board there. So we start with the reading. There is only single reading here. There is a little fluctuation in the voltage, so the reading is fluctuating a little, and it comes out to be 5.77 or 78. So it should be nearly approx to 6. So we can say that we have verified the Thevenin's theorem, because there is a little bit chances of error due to the change in voltage fluctuation conditions. So the reading is coming out to be 5.78, which is approximately near 6 volt. So the B.Tech is 5.78 volt. So we have verified our Thevenin's theorem. So this is all for the Thevenin's theorem. And if you have any queries regarding this, you can ask me questions, and any problems regarding the experiment, you can ask me question. You are free to ask questions. So students, please do take care of yourself, and thank you.